So our next talk is about SD card and SD card reverse engineering. I'm really eager for that because I think that's going to be really interesting. So please welcome Bunnie and Xobs for their talk on SD memory cards.
All right, thanks. It's nice to be in Hamburg at the Congress again, and this is an absolutely massive hall. Holy cow. Today we're going to talk to you about the exploration and exploitation of SD memory cards. And maybe get you started with how we got into this whole project in the first place. Actually, many years ago, we were working for a company called Chumby, and we had a production run. We were using microSD cards as the boot media for some of our devices that we're selling. And we found that some of the cards were not running properly. They were not booting correctly, and we're having boot issues. So we went and we looked at the cards and compared them and found certain anomalies in the way that they were labeled, in the way that the logos were printed, and sent them back to the vendor. And we said, hey guys, these cards are not seeming to be consistent with the labeling and the quality standard. Vendor came back and said, no, these are totally authentic cards. So the next thing we do is we go ahead and we buy a bunch of fake cards and a bunch of real cards, and we tear them down. We put acid on them, reveal the insides, take a look at what's on the inside, and show the vendor that their cards actually have part composition looks exactly like the fake cards that we get on the market versus what the authentic cards look like. At which point they come back and they say, well, okay, we'll take the cards back and give you the real cards, right? But at the end of the day, one of the interesting things that we found was that inside every card was a microcontroller, a small embedded device to manage the flash, right? It typically tends to be an 8051 or an ARM7 type CPU. It's a few square millimeters of silicon, and as a former silicon guy, I like to always think in terms of like what's it cost and so forth. And so back of the envelope calculation, about 25 cents or so is what it adds to the cost of the card. If they're able to get the flash, the microcontrollers directly without a markup from the fab. You compare that to the die area of the flash, 100 square millimeters, which is about the size of this piece of flash memory here. It's about $3 cost. So it's a very minor cost add compared to the cost of the flash. And to put it in perspective, if you were to go ahead and at the wafer scale, so take the raw flash wafers and use like a high-end sort of wafer probe testing station, which costs about $1 million to purchase. If it takes you 30 seconds to test that, the amortization of that tester alone for 30 seconds will cost you about 45 cents. So in fact, economically speaking, putting a small controller on every single die, whether the die is good or not, and using that to help run the test and determine what's going on the inside actually makes sense. And so a little bit about why the microcontroller is actually necessary. One of the things that maybe many of you are aware of, or maybe not, is that flash memory is unreliable, like incredibly unreliable. You don't want to look under the hood and see the sausage that's inside. You're not really storing your data, you're storing a probabilistic approximation of your data. They do a lot of workarounds to try and work with this. For example, ECC. So your bit rate may be absolutely terrible, but they're using now very sophisticated high density codes to go ahead and try to correct block errors and bit errors and so forth. And also, you have lots and lots of bad blocks. Flash memory is really, really cheap now. It's 0.1 nanodollars per bit, approximately, right? And so things have come a long way since back in the day. But this is only achievable because every piece of silicon that comes off a wafer is sold. Nothing is thrown away. So normally if you do like a run of CPUs or something, you have a good margin, you can go ahead and afford to bin out some 10%, a few percent, and throw it away. These guys basically have to sell every chip that's made, otherwise they lose money, and they're still probably losing money half the time anyways. And so they have a workaround, which is bad block remapping. And so sometimes some chips are sold to you with 80% or more of the blocks bad. So people will make chips that are supposed to be 16 gigabytes of flash, only 2 gigabytes are good. Well, guess what? They sell it to you as a 2 gigabyte device, and they just have to remember which blocks are bad, and hopefully your data doesn't end up in those bad blocks. Also, with more programming erase cycles, the memory will actually degrade over time. It can no longer reliably store your data. So this graph on the right here shows you sort of with process node, so from 50 nanometer, 30 to 20 nanometer, the number of program erase cycles that you're able to get, and also plotted versus multi-level and TLC flash. And in fact, the latest generation TLC devices are only good for less than 1,000 program erase cycles. So you need to have something in the inside that if you just keep on pounding a particular sector, say you have a swap disk or something like that, which all maps to the same logical sector, you actually want to wear level and move those blocks around the flash so you're not constantly pounding the same sector. Otherwise, you'll find your SSDs have a very short lifetime. So there's a question, so why do it at this layer? Do we have to put a controller inside every flash device? Why don't we put it in the OS? Why don't we just throw it in Linux, right? Why don't we do it at the application layer, right? And there's some places where these happen. So there, back in the day it was JFFS and YAFIS where they did bad block management and even revealed some of the details of ECC to the Linux kernel layer. And some applications, like if you're building a rainbow table, you just want massive amounts of flash. You actually don't care if the data is not completely perfect. You just want lots and lots of cheap flash. So you just take raw flash, throw data in there, and just hope it comes out okay. But these are very, very special cases. Typically, flash geometry, the actual memories itself, the geometry of the fabrication of the chip, is changing every 12 to 18 months at a very fast pace. And with every new process generation of making flash chips, there's a new set of ECC rules. They use stronger and harder ECC. There's new page sizes and block mapping algorithms. And this is an intensely cost-sensitive market, so the lowest cost and highest performing flash memory will tend to have very proprietary specifications around what you're required to do to make the flash actually appear to be reliable. So if we were to go ahead and push this up the stack a bit and say put it into the OS or at the application layer, these you would have to have NDAs signed and specs going back and forth and people pointing fingers at each other over it's a driver bug or it's a hardware bug, and it'll take 2 years just to ship a product, right? So the easiest thing to do is to just, like again, 15 to 30 cents solves the problem, throw the algorithm in the controller, and present the illusion of perfect data to the user. Now the concern is that now that we know that these microcontrollers are not going away, and they're in every flash device, whether it's a USB disk or an SSD or microSD, eMMC, all the things that we use to store memory inside our mobile phone and whatnot, we know there's a microcontroller, it has to stay there. The question is like, what does this controller run? Can it be hacked? Do I trust this? I've actually created the perfect setup for the man-in-the-middle attack. We've just invited in someone to go ahead and sit in between our data, and we just trust them to do whatever they want to do. And so, we turned in the fakes quest, and we got handed a new quest, which was to hack an SD card. We decided we would go ahead and search for an SD card, and just to demonstrate that we can run some code on it, maybe make an LED flash or something. Particularly challenging because these controllers are very obscure. There's virtually no public documentation available, no data sheets. People that haven't even heard of the manufacturers like Apotec or SkyMedi, SMI, these guys, they make millions and millions of microcontrollers that you probably have them in your pocket right now, but you've never heard of them. And so the bulk of this talk is going to be our story about how we got into these microcontrollers, what we found, some of the hardware tools we developed. I'm going to focus on that aspect. And xobs here will talk about the software tools and the static code analysis we did to discover backdoors in controller structure. So the first step is to acquire targets. And we wanted probably a good wide selection of the most fakest, worst cards you could find. Because they tend to have, the rattiest construction, and there's one place in the world to really go find these, which is Huaqiangbei in China. I don't know, how many people here have heard of Shenzhen or Huaqiangbei in China? Oh, good, good. I'm very good. That's very pleasing to see that people know about the area. It's like my favorite place. It's like I'm like a pig in shit, like rolling around their components everywhere. This is a typical picture of a vendor booth there. So this guy is selling flash memory. He has a little glass stall, and inside of it, if you could see from the picture, it's packed like with probably 50,000 flash chips or so. You can walk up there and say, "Hi, I'd like 2,000 flash chips." You negotiate price in Chinese. You hand him some cash. He gives you something, and it's cash and carry. If you got fake ones, it's your fault. If you got real ones, great, you got a deal, whatever it is. So wandering around the market, there's little vendors here who sell lots and lots of SD cards of questionable origin. Lots of them are used cards or fake cards or whatever it is. This one's, proudly advertising that can give you a 512 megabyte SD card. Very exciting. And we bought a bunch of them and tore them apart. Eventually, I got very good at using nothing more than a pair of wire cutters to extract the circuits on the inside of an SD card without damaging them. And you learn all sorts of little things like how to tell if a card is fake or real, or like what the construction of the inside by just sort of feeling the card and bending it a little bit. This is what's on the inside. So there's generally a couple broad categories of SD card construction we found. On the left is what we call a discrete construction. They have a standard TSOP flash memory that's soldered onto the board. We show it removed on the left, and a little spot where you see the red circle is where the microcontroller is a chip on board with a glob of epoxy on top. So if you knock off the epoxy, you can see the chip beneath it. One interesting thing, you'll see this little bit of cut tape they stuck on the inside there. That's actually not a mistake. They actually put that on the inside to make the card feel stiffer, so that if you're doing the feel test to see if it's fake or not, you don't know. And it's a very cheap way to do that. And then on the right-hand side are the what do you call the monolithic constructions. Typically the higher end, more reputable vendors like SanDisk will use this construction. Everything is molded into a single piece. There's no opportunity for tampering with the flash or replacing it with fake flash. But you will notice on the back side there's a set of test points, those little gold dots on the bottom. And if you put up oscilloscope on it and you see the card boot, you can see actually, in fact, identify the ALE, CLE, write enable, chip enable data pins for all the flash on the inside. And there's also a set of pins which look suspiciously like JTAG pins for a controller. One thing, sort of interesting thing is, of course, I like to take apart stuff and see what's on the inside, and so we want to decap some chips. Some of these overmolded chips are actually really poorly constructed. So the first thing, my instinct was to go ahead and we have to go find some nitric acid and get a safety goals and a fume hood and everything like that to go and digest these. Xobs was like, I don't know, I think you can just take this off with a screwdriver. I'm like, nah, you can't do that. So he starts playing with it and starts flexing it, and like the top just pops right off. And so you can see, like, on the upper right-hand side is the top. You can see the imprint of the chip and the PCB and the plastic where it was bonded. And pretty much the perfect intact chip and the controller and so forth all just kind of coming out. So that was the easiest decap job we ever did. There's some pictures of some of the hardware that we built for tapping. One of our first generation, we wanted to tap the monolithic cards, so we built a little jig that could hold the SD card in a frame, and then it would press down, and there would be these spring-loaded pins that would touch down onto the test points in the back. And then this would then hook into another board that we had actually made ourselves called Covan. It's a little 800 megahertz Linux board with an FPGA on it. We could go ahead and monitor the SD pins and the flash internally using this mechanism. That turned out to be not the best approach because it was very hard to get the alignment just right on the cards. There's a lot of mechanical issues. So for the second generation, we decided to build disposable tap boards. These are actually flex PCBs. So they're, I have samples here, which I can show people if they want to come up afterwards. But they are flexible. I should take this out. So they're flexible, and they bend over on themselves like this. So the general idea was that there's supposed to be in the region there, which looks like the footprint for a TSOP. You can go ahead and solder that in place of the flash memory, and then you would flex the board over onto where the SD pins were. And the fact that I was flexing when we had a long piece meant that we would accommodate a variety of sizes of boards. So we didn't have to lay out just one board. We could use one tap board for multiple cards. This is what the cards look like when they're actually mounted. So in the middle, kind of on the upper middle, you can see when the SD cards look on the inside. We took off the flash. We went ahead and put the tap board in place, looped the flex back over on the backside, and then put the high-speed header on it, plugged into our Novena platform, which we designed ourselves, has an FPGA and so forth, a high-speed header. And then on the left, you can see we built a version for doing monolithic chips as well. This is what the tap looks like in system. So again, on the left-hand side, on the lower left, there is the tap with the SD card mounted on it. And then above it is, some of you may know this better as our open source laptop motherboard. But we actually use it as a general hardware development platform for all kinds of things. When you have a hammer, everything looks like a nail. And so it has, this one here has an FPGA, 256 megs of DDR3, a quad-core ARM CPU on the inside, and all the other fixings that you need to go ahead and build a functional system. The tapping system diagram, you can see here, this is sort of like a block diagram of what's on the inside. The green stuff is all in the FPGA. The sort of the pink stuff on the right, or salmon or orange, I don't know what it's linked, is the Linux host. It talks through a memory mapped register interface. And then on the bottom side is where the SD card is. And then for the SD card, we can either override the memory of the flash chip and do what we call a ROMulator. We use the DDR3 memory to go ahead and emulate about 256 megabytes of flash memory, or if we want bigger, we just loop it over and over and over again and just record when addresses are out of range. Or we can go ahead and just do like a logic analysis with it. We can go ahead and capture traces of the microcontroller talking to the SD card and the memory internally. So what this system allows us to do is, from the Linux host, we can go ahead, control the SD interface, observe what the controller does to the flash, modify the flash on the fly without the controller knowing, and see what the controller does in response to that. So it's a very good system for automatically fuzzing and scripting and figuring out what these controls are doing on the inside. And of course, a tool that is indispensable in this is a ROM reader, the humble ROM reader. And this was actually the beginning of one of our most successful threads in figuring out what's going on. We found a discrete implementation that luckily used SLC memory. So SLC memory is a very easy to read with ROM reader type of memory. We found exactly 2 cards in the whole market that was still using SLC memory. And it's of course easy just to strings it and cat for it. We took a look around first thing and found this string on the inside, China Buildwin SD controller. Go into Google, plug in a little bit, come out, okay, there's a company called Apotec that makes this, likely in 8051, we figured probably the AX211 microcontroller. We figured that somehow that firmware that's on the memory card had to get there. So there has to be some sort of factory tool for flashing that firmware in. And so we went ahead and we did a little search to try and figure out, can we find the tool that they're using or whatever it is. And this is where I'll hand the presentation over to xobs to talk about that part.
So if you ever need to hack on a dodgy Chinese product, there's a website that I really recommend you going to. Baidu is the Chinese equivalent of Google, and we figured that it was an AX211, and so we typed that into Baidu. And the first site hit up there is for a car. The second one, I don't know what that is, looks like a phone. The third one is an AX211 SD, and you click on that, and you're brought to this page, which will actually let you download the software to program the card. That's a pretty lucky first step. So you open the programming tool, it runs on Windows, and you're greeted with this. If you actually translate this, there's some really interesting strings.
Go ahead.
Yeah, if you actually translate this, you can figure out that this is setting every parameter for the SD card that you want to burn. You can set the manufacturer code, you can set the serial number. In the bottom right there, you can actually set, right now it's set for auto, but you can have it manually specify what it reports the card size to be. Which, if you're making counterfeit cards, that's a great box to have. Now we're looking through the actual program and we notice that there are some strange file names. This is what the directory structure looks like, and there's the normal Windows executable, and then there are these these files called, there's a5scan.dll, a5testboot.dll. What's a DLL file doing in a firmware program. We thought, maybe if you open it up in IDA, it's not x86 code. What is that? We decided to open up it and actually read it as 8051 code, and we were greeted with this, which, if you look at it, that's actually completely legal 8051 code. There's just one problem with the 8051 byte code. This is where I got this firmware file from. That's just random noise. It's completely legitimate 8051 executable code. The CPU will try to execute this, and it may get somewhere, but not useful information. 8051 has a really dense instruction set. If you look at this, is every single one of the 8-bit opcodes. There's one opcode that's undefined. Yeah. Anything else will decode to an instruction. So this is our data sheet that we found. It's one page. It's in English with the data sheet reproduced in Chinese. And if you zoom into the English, you can get all sorts of interesting features that this has. A couple of ones to call out. It's got supports SLC or MLC. Those are the two kinds we saw. It's actually available in an actual chip package in addition to the die form that we saw from the markets. It's also got a 32-bit RISC CPU, which kind of puzzled us for a while. We thought the 8051, that's 8-bit. What's up with that? Anyway, the actual programming process goes something like this. There are 3 devices involved. There's a Windows programmer. There's what we think is an 8051 programming jig. We never actually saw this device, but we saw by disassembling the Windows programmer, we managed to figure out kind of what this thing does. And then there's the actual 8051 SD card, or the actual AX211 SD card that is under test. And just in terms of the program, the main process, what happens is you open the programmer program, Windows application, it loads the firmware onto the AX2005 programming jig. You say that you want to burn a card. It then loads a 512-byte testboot.bin into the AX211 SD card. The SD card responds ready. It sends over a flash scanner that actually verifies what the flash size is. It tries to determine what brand of flash you're using. It does a bad block scan. And then eventually the the Windows software uploads a programmer. Then it uploads the bin file, and then you have an SD card that's all programmed. And it does this all over the SD protocol. And I'm just going to go into a little bit about this because it comes in really handy when you're trying to access this card. The SD protocol has 3 main signals. There's command, there's 1 to 4 data signals, and there's a clock. And the way it works is every time the clock signal goes low, it samples the command or data signals. And every channel is protected by the command signal uses CRC7, and the data channels use CRC16. There's 1 CRC16 per data channel. Just as a side note, most cards also support SPI mode, which if you're going to connect an SD card to like an Arduino or something like that, you'd talk to it in SPI mode. But everything we did talks to it in normal native SD mode. Now in SD protocol, there are 64 possible commands labeled 0 through 63. Some of the interesting ones, command 0 is reset, and that's the very first one you send to a card when you want to talk to it. It's supposed to not respond at all when you power it up until you send command 0. Some of the other interesting ones are command 10, which is the get card identifier. There's command 41, which is like we're going to escape and run in a different set of commands. But there's also these, they're called class 8, commands 60 through 63 that are explicitly reserved in the specification for manufacturer. So that looks pretty interesting. Every command also takes 32 bits of argument data. So if you look at the bottom, you send the command followed by the argument data, followed by the CRC7, followed by just an end bit. And the CRC7 in SD mode must actually match the data. When you're running in SPI mode, it actually turns that off. But for us, we had to get the CRC7 correct. Now when the card responds, it sends another 48-bit response back to the host. It sends the start bit, the transmission bit, the command that you sent it, and then a 32-bit card status field, which has this really interesting bit in there, the illegal command bit. So if you send a card a command, and it's not in a state where it can actually respond to it, it will respond with this invalid command bit, which means you can now fuzz it. You can send random commands, look for that illegal command bit, and if you get either a freeze or a not illegal command back, then you found a valid command. Great. So what we're going to do is we're going to fuzz the sequence. We're going to reset the card. We're going to power it down, power it up, send the command 0 to actually reset it. Then we'll send a random command with a random argument, check for a response, and if it doesn't respond, or if it responds with a not illegal command, then we have something interesting going on. Maybe it's code execution, maybe not. If it doesn't respond, it probably means the card crashed, which is great. Now, there's something interesting. Bunnie showed this picture earlier, which shows the AX211, nicely labeled, right in the middle, with no NAND attached anymore. The idea was you're supposed to use the ROMulator that we wrote to emulate the ROM. But the interesting thing is, with this particular card, if you reset it, set it to command 0, it'll still respond to some commands. It'll respond to command 0, because that means go ready. It will respond to things like turn CRC on or off. But the go ready command, the hey, I want to actually read the file system command, doesn't work, because of course it doesn't have either firmware or any NAND flash to store it on. So the actual fuzzing, we didn't get much huge success just because there's 64 times 2 to the 32 possibilities. But the nice thing is the fuzzer can actually run on its own and just let us know if something's going on. So we can let the fuzzer run, and we could try a different approach. So we're going to look at that AX2005 firmware burner to see if there's anything interesting in there. And you open it up, and we notice it's bit-banged SD. This is also 8051 code, and this is a subroutine we found that all it does is it checks for a bit, it turns a line low, waits 1 cycle, turns the line high. Now that is an SD cycle. That's it clocking in an SD bit and then releasing the line high. So that's pretty good. Based on that, we know that it's actually SD. Now, in looking at the firmware, we notice somewhere up the stack that there's actually this string, APPO. Well, we know this is an Apotec card. That's kind of an interesting string. It's also 4 letters. It's also preceded by constant 63, which is squarely within that command reserved for manufacture. That's promising. So maybe the knock is command 63 followed by APPO. And sure enough, we send that, and the card seems to respond. It doesn't say invalid command. And if you send it 130 bytes, I say, it will not respond if the CRC16 is valid, which probably means we can run code. Great. We have a problem. What code do we run? Like you have a CPU, you're executing code on it. Now what? Well, we know that they use the SD protocol to actually run code and get a response. So let's just go ahead and do that. And the nice thing is we have example code. So we have the test boot that it sends first. It's 512 bytes. It's easy enough to analyze. It tells us the entry point, which is really important because that could be anywhere in RAM. And it also contains the SD state machine that they communicate with. We also have the firmware dump that we did from the original card. And this is pretty interesting. If you use IDA and you highlight a particular function, it'll highlight everything else that is the same address. And if you look at the SD card spec over there, I've highlighted all of the reserved commands for the first 14 possible SD card commands. And you'll notice that the pattern of yellow boxes matches up directly with the pattern of functions that are jumping to the same address, which probably means that this on the left is the SD card state machine for the actual live SD card, which is another good source of, they do it there, why don't we do the same thing? So the first thing we do to write a debugger is we borrow testboot.bin, and it doesn't work. We don't already have a debugger, so we can't figure out what it does. And the first thing I want to do in this, maybe we can wiggle a pin, get some sign of life. So we decided to go hunting for a GPIO. GPIOs are you write a byte, the line goes high, you clear the byte, it goes low. It's probably going to be 1 to 3 registers. One register is definitely going to be the value. Another register might be to set or clear a pull-up, we don't know. Another one might be if a pin can have multiple uses, it might be a set pin function register. And what we're going to want to do is we're going to toggle them low and high and low and high so we can look for some sort of, hey, this is wiggling up and down, that means that it's alive. So we'll write a fuzzer, another fuzzer. Fuzzers are great. And the fuzzer is going to take a random number and poke it into a random value in the special function memory mapped register area. It's going to delay a while. It's going to change that special function register value to a different value. It'll delay again, and it'll repeat. And if this is actually working, we should be able to see on the host the line going low, and then high, and then low, and then high. It's just kind of a hey, I'm here. And so we let this run. We let it run for, I think, about 3 hours before we finally got a hello world that worked. So let me explain this. What this does is this moves the constant 0, 0 into the special function register EF. It sleeps. Then it moves the constant FF into the register EF, sleeps again, and it jumps. So that's just writing 0F out the GPIO. And when you read the pins, the SD pins from the host, you can see it going up and down. It's going from W to G to W to G, which is great. We now have hello world. So we know that we have code running. We know we have some sort of 1-bit bidirectional information. Great. It's enough to actually get code working. You can try things by comparing the testboot.bin and sticking this hello world in there. You can figure out where it's going. You can figure out which jump sequences it's hitting, which is not. And eventually you can build this up and you can get bidirectional SD communications. And so we wrote a debugger around this. What we do is we send a command with 4 8-bit arguments, and that ends up getting that fills that 32-bit SD argument. The card looks it up in a jump table, responds, sends a command back with the same value and a 4 8-bit values, and it goes to 1. And so we implemented a debugger that has basic peek poke. You can do GPIO detection, IRQ status. We interfaced with the NAND emulator so that we were able to determine what's going on with the how the NAND registers work. And we also found, maybe the data sheet was right, maybe this is a 32-bit CPU, because we found these opcodes that just, what's going on with there? Turns out A5, that A5 CPU opcode is actually a 32-bit command. Standard 8051 does not define this at all, but it's all over the place in the AX211 firmware. And it's always in the format of A5 plus 1 byte, or A5 7 something, and then another byte. Which brings us to the question, what is this chip? Is it 8-bit or is it 32-bit? We found that these 4 registers are 32 bits. We wrote an xop debugger command that we can use to send random arbitrary A5 instructions. And we discovered, at the very least, we found 32-bit clear, not increment and decrement instructions, which when you're writing a CRC16 engine in software on an 8-bit CPU are really useful to have. But there's a whole huge opcode space that we never actually looked into. So now I'm going to turn it back over to Bunnie, who's going to talk about the AX215.
Thanks, Sean. And so, again, there was a link earlier to a GitHub repo where you can go ahead and see all the code that we have for the debugger and running it, and you can go ahead and actually replicate most of this. The code is custom to our Novena platform, but because the actual GPIO protocol to SC interface is doing bitbang, you can port it to a Raspberry Pi or an Arduino or something like that if you want to go ahead and play with these. Which leads us to a point which brought us to the AX215. The AX211, as I had said earlier, we found 2 of these in the market. They're really old. And when we contacted the vendor, they said, sorry, these are end of life. You can't buy AX211s anymore. We're like, that would be really lame if we go to CCC and talk about a card where there's only 2 in the world that you can hack. And so in preparation for coming here, we asked them what is the most recent card that they have, and they said, well, it's AX215, and we say, okay, that's fine, we'll go ahead and look at it. It's basically, very similar to AX211, it's faster, runs at 90 megahertz, has more GPIOs, has a slightly different, actually radically different special function register map, the hardware register mappings, and we went ahead and repeated the fuzzing and the activity to bring up the debugger on the AX215, so we forward ported the debugger to the AX215. There's one really important difference is that they got a little bit smarter and obfuscated their code binaries that were stored in these, the things that would be used in the factory programmers. But this is the whole routine that they use for obfuscation. They came up with some, I don't know, crazy, it doesn't even look that good kind of byte shift swizzle kind of thing. But we can just pull it with IDA and get it to run. And so we wanted to make sure that, sorry, let me say it. Because it's not obvious what controller is mapped with what flash when you buy a particular card, it's very hard to say, just go ahead and buy like bazillions of cards and keep trying them until you find one with Epitech control on the inside. So we went ahead and we brought along a couple hundred SD cards to the talk, which they're actually very cheap. They're about €1 a piece. So we're just going to leave them at the front of the stage after the talk if you want to grab one. you can grab one and go ahead and try to play with it and see if you can get something to run in the microcontroller. Because I'm a very big fan of being able to run code on any hardware that you own, including your SD card. So, so we'll just leave them up in the front. Please only just take one. Don't try to take a whole handful of them, because we only have a couple hundred of them. So, so now, time for tinfoil hats, right? So now that we know that we can run code on these things, what are the scenarios? Well, there's clearly a scenario for eavesdropping. This is the case where, unlike the people who are selling you fake cards, we actually give you a card with much more memory than we say we have. So there's 8 gigabytes in a card, we say we only have 4. And then when you go ahead and you write some files in there, we look for properties in a file name, we take a copy of it, we put it inside of our backing store, and you can go ahead and do everything you want from the file system OS label to erase it. You can fill the card with random data and erase it, but you'll never touch the stuff in the backing store. So we can do eavesdropping with this mechanism. There's a time of check to time of use attack where, for example, a file can be presented in one version for verification, another for execution, which is an opportunity for all kinds of fun manipulations. And also because SD cards are so massive, I mean, it's not inconceivable to also do things like selective modify. So 4 gigabytes is plenty of space to hold lots of versions of particular C files. So if you were to go ahead and try to copy some source code on there, we can look at the name of it, your random number generator, whatever it is, and say, well, if it's a random number generator, we'll go into our huge library of random number generator C files, go ahead and swap one in and actually store this one instead on the card, so the next person who reads it out gets a different version of the file. We can go ahead and modify keys, for example. It's very easy when you know where the keys are to go ahead and change a few digits and make them very insecure, factorable, and so forth. So there's a lot of scenarios where if you want to put on your tinfoil hat and worry about what's going on, we've always sort of trusted that these controllers on the inside are running, but they're running correctly and doing the right thing. But currently there's no protocol or no method to attest to the code that's running inside of these things. We can't inspect them, they're full black boxes. We just trust them that we put our secure data on it and everything's perfectly fine. Other directions that we could go into is there's the this note here that we've been pointed to. The Samsung actually had pushed a firmware patch to eMMC cards, which are basically SD cards in BGA form factor soldered onto a motherboard inside Android device. I think they're in like the Note or something like that. And what was happening was that during certain operations, the devices would brick. They would just not come on because the SD controller would go tits up. And so in order to fix this, they went ahead and pushed a patch to all the cards. You can run it. And so some enterprising people were like, well, what's inside this patch? They're looking inside. They find there's ARM code on the inside. Again, command 62, which is right inside the reserve space, a few bytes that look like Knox sequences. You can go ahead and bring the card into RAM reading mode and so forth. So these are cards that are known to be in particular mobile phones, which have a vulnerability that was essentially published by the manufacturer to go ahead and let you update the firmware. Another sort of future direction is TLC and MLC flash. So this gets into a bit of the details of how flash memory works. TLC stands for tri-level cells. They actually store 3 bits per cell, so it's 8 voltage levels per cell. They're great for density. They're terrible for reliability. They actually have a problem called read disturb, which is, if it sounds disturbing to you, it is. It means that if you keep reading the data, you can actually disturb adjacent data and cells from these particular memory cards, right? So that not only does the controller have to control like where the bad blocks are, it has to say if you've read a block too many times, we have to read it back and refresh the data again. In order to minimize this problem, they have to do some manipulation of the data that's stored on the card by XORing it with a scrambling algorithm, which helps distribute the states across the data. It's data dependent. It's proprietary algorithm. Every vendor has a different algorithm. But as you can see, the data is highly structured. I just took one of the raw dumps we have and put it into an image viewer. And you can see there's a lot of structure in the code. So it's not really it's not for a security type thing. It's more of just making sure that the statistical properties of the data stored is consistent with something that minimizes the read disturb issues. So sort of on a wrap up, so SD cards and also any sort of flash type memory will contain a fully programmable microcontroller, perhaps a very powerful microcontroller. This applies to SD cards, microSD cards, eMMC, SSD, USB controllers. The controller program we have demonstrated is modifiable via special host commands, and these are typically not locked out because of the complexity of the flash memory space. You want to be able to mix and match controllers to the newest, latest, greatest flash chips, and they can't really burn the code into the flash chip. They have to have a way to load code into them and oftentimes patch them in the field so they don't close the hardware backdoor. This, on the black hat side, is a potential for man-in-the-middle attack scenarios. On the sort of the white hat side, which is what really got me into the project, is this is a potential for an extremely cheap microcontroller for fun projects. I couldn't stand up here and hand out Arduinos. They cost like $20 a piece or something like that. They're too expensive, but these are €1 a piece. These cards only have 128 megabytes of memory on them, or so they say. And the thing is that if you can control the SD card, it is IO limited, but it makes a great data logger, for example. You can go ahead and bit bang I2C or SPI and have a single chip data logging solution for €1, which is very exciting to me. We want to just give a special thanks, a shout out to Mudge, who had created the Cyber Fast Track program, who had enabled this research and many other good things. Some are still yet to come. So thank you, Mudge. And now we're going to cut to a demo, which we do have time to allow for this. So can we get the camera over here? And maybe get the camera showing onto this device here.
This device?
Yeah, this one here. So there's lots of stuff on the podium. Can we get the view on the, there we go. So we gave this presentation on Novena, the laptop we built ourselves. And so you can see, as I mentioned, this is a quad-core ARM device, and it's running, this one's running Ubuntu, this one's running Debian, so you can have your pick. No religious wars here. And here is actually we have the SD card plugged into an adapter, which is going into the FPGA, which is on the main board, and xobs will go ahead and demonstrate sort of the, how this all works. Can we actually get like a picture-in-picture? For what on the console screen as well as. All right. Cool. So. There you go. Perfect. So he's going to go ahead and configure the FPGA on the inside with the firmware file to go ahead and tap it. It's actually just, we just cat the bit file to dev SPI. And then we go ahead and we can run the debugging software. Give it the argument of the binary file to run. Why don't you go ahead and give them an explanation of what's going on.
All right. So the first thing the debugger does is it goes ahead and tries to knock. You could see because the card wasn't plugged in all the way, there were a few times it tried where it didn't actually communicate with it, but eventually it managed to load the debugger and check the card communication. So it actually sends a random set of packets back to the card, and the card is supposed to echo random packets back. Then it dumps the RAM of the SD card. It dumps 512 bytes, which hopefully is our program. And after that, it looks through for some fix-up hooks, just prints it to the screen, enables some interrupt service routines, and presents us with a shell. So I've got a few commands you could run. There's hello, peek, poke, the usual ones. Jump, so you can load code in with peek or with poke and actually jump to it. There's the IRQ, which is what we use to figure out what the IRQ table does. This card has 5 IRQs, 0 through 4. IRQ 0 we know just from 8051 is reset. If you look at this, IRQs 1 and 2 they're not 0. And if we query the IRQs again, they keep going up.
Right, so these are counters for the number of times the IRQs fire, just to clarify.
Yeah. So, yeah, because these numbers keep going up, it means IRQs 1 and 2 are probably have to do with the SD communication. Other things we could do is you can dump the special function registers. One of the nice things about 8051 code is that there are only 128 possible registers. Makes it really easy to fuzz. What else? There's also an external opcode command. So I mentioned this in the talk, where you can actually have it execute an arbitrary opcode. So we'll send it A5 and then 1D. Sorry. There we go. So back, so we can send X to op and then 1, 0. Stats, it's IRQ. You can see that we now have -1 IRQs. That's because X to op 1, 0 is the invert opcode. And so using this, we can actually fuzz all of the opcodes on the system and basically generally figure out how this card works.
And so just to clarify, the IRQ counters are actually using the 32-bit registers that we discovered inside the 8051, because you want a bigger than 256-bit counter. So I'd use the xtop codes to go ahead and manipulate these extended instruction sets inside the 8051 to implement the IRQ counters. There's a disassembler in here, right?
Oh yeah. We can actually disassemble 4700, so we'll disassemble 64 bytes. At aux 4700, which is the entry point for the debugger. When you load firmware, it gets loaded to address 4700. And if we disassemble that, we can actually see there's the opening to our debugger plus our jump table.
Yep. Cool.
All right.
So hooray, the demo gods are kind. Yeah, so this thing worked amazingly. I guess we can open the floor to questions now. We should have time now for questions. So thanks, everybody. Thanks for coming.
Okay, thank you very much. And yes, we have quite some time left for questions. So as always, please line up in the room, in the middle of the room. Or if you have questions from the internet, please write them on IIQ or Twitter, and we will ask them live in the room. So we please have a question from microphone number 1.
A very short question, USB sticks.
USB sticks also contain microcontrollers on the inside. In fact, if you look at a lot of the data sheets, the ones that are made for SD can also be used for USB. You just throw the USB PHY in. They're virtually identical in terms of the composition.
Actually, to follow on that, the AX215 factory programmer actually uses an AX216 USB controller in GPIO mode. So they actually use one USB controller to program the SD controller.
Okay, microphone number 2, please.
Hi, thanks for a great talk. I'm really not knowledgeable about the whole topic, but I wondered if you have looked at the host side. Like if you have a laptop that has an own microcontroller for communicating with the SD card, right? Then I guess there are microcontrollers for which some exploits are known. Do you think that like the microcontrollers in the SD cards are powerful enough to basically write some malware, and then you have some SD card, you plug it into your someone's laptop, and you basically do evil stuff there? Because you only talked about man in the middle right now, and I think you might be able to do even more evil things.
I see. So more like an active attack where you plug the card in and
Yes.
stuff comes back. I think, yeah, I mean, it could be possible. Part of the thing about the SD interface is the host drives the communication. So if you try talking back to the host, it doesn't really do anything. But I could imagine on the USB cards there could be some other potential venues for attack and so forth. But I mean, there are a lot of, I mean, to your point, there are a lot of embedded microcontrollers within every system that we don't really see. So in fact, like a lot of laptops, the SD readers actually implement itself with a USB device. So when you plug the SD card in, it enumerates as a USB device. That's because there's a microcontroller on the inside emulating the SD interface to the laptop, which itself can be another venue for potential exploitation. So there's a lot of these layers and layers that we just sort of trust in everything.
Microphone number 1, please.
I'd like to know what is your guess? Has this type of microcontroller already been used, be it for malicious intent or for example, some proprietary measures like DRM in the wild, aside from just being a microSD controller?
What's our guess for that? I mean...
Or do you know?
No, I don't know of any solid instances where it has been done. I do know that when we've been to the factories where they burn the firmware in, and you can basically just walk in and go up to the burner and replace the files on it. I mean, like literally there's chickens running through the factory and shit like that, and like there's no security, there's no badges, you're like, oh yeah, here's the burner, right? So, like and then they make these things and they ship them all over the world, so it wouldn't be hard for someone to do that. Whether it's been done or not, I don't know. So.
Okay, microphone number 2, please.
Hi, I'm just wondering why you didn't mention UBI. Because you talked about the host layer and said, yes, NJ has 2, but we have UBI.
Oh.
Because we have UBI because it's well known that all these on-chips things are very, very bad. And if you're building a sane embedded device, you have to use raw flash and UBI. Otherwise, you're toasted.
Well, the actual answer to that is because we stopped using NAND flash just before UBI became popular. So by the time that was the go-to standard, we were already moving to the SD card stuff, and we just pretty much haven't looked back.
Okay. Please look at it. It's very nice.
Okay, fair enough.
Okay, another question from microphone number 1.
Yeah, you mentioned that the code in the controller is not protected because of reasons. Is there a possibility to protect it? Is there a lockbit or something? Can I flash a very special firmware and then protect it from being overridden?
I think when we looked at some of the SanDisk cards, they look like there is some kind of maybe protection going on of some type. This work was looking for the path of least resistance to demonstrate the proof of concept. It doesn't mean that all controllers are this bad per se. I don't want to use bad in a pejorative term. It's just that when you're a manufacturer of third-party controllers and you're not like SanDisk where you can make the controller and the flash device yourself, you have to make it so other people can modify and load code on it, so you get more market share by being very open and sharing within that group of people the loading standards and so forth. And so because at SanDisk, if you look on the inside, the die shots of the controller say SanDisk, as well as the die shots on the flash say SanDisk. Presumably they're doing a lot of mating on the inside and mixing and matching, and they can lock it down a little more carefully. But presumably also they're not, I mean, they're definitely not crypto grade.
Yeah, what I meant was primarily from the tinkerer's perspective. If I buy one of those cards, can I protect it?
Oh, can you protect it? No.
Okay.
Okay, so do we have any questions from the internet?
There is one question, and Root asks, he had experience with reduced card space on 3.8 gigabyte cards toward 2.8 gigabytes after he changed the file system to extended formats. About 3 times the same reduction, which was apparently an amazing experiment. So I'm not sure exactly what he's asking, but he writes, what kind of flash NVRAM would you recommend?
She's looking for a brand recommendation?
Yeah.
I don't really endorse any in particular. They all have problems. Just I don't know. I mean, like even the big ones, you can get fake ones because I mean, again, the industry runs on such tiny margins. These fabs, basically, if they don't run at exactly 100% capacity, selling on a good day, they're losing money. These memories are so incredibly cheap. So everywhere inside the supply chain, there's a ton of pressure for people to cheat, take old material, scrap it, and then recycle it in. Which, okay, if you're one of those people who are like concerned about e-waste, this is great. All your flash is being recycled. There's no flash thrown away. You can resell it to you as a perfectly brand spanking new card. But at the end of the day, even I mean, the intention of the manufacturers is very good, but the supply chain doesn't execute as well. So I can't say for sure which one is going to be the best to buy.
Okay, a question from microphone number 3, please.
Hi, I was wondering, I really like the work you've been doing on SD cards, but I'm also curious about how that applies to other forms of flash, particularly things like MTD devices on Android devices. Do those also have these kind of logic layers in there, or is that raw flash that's handled by the OS?
No, the Android devices will typically use iNAND or eMMC, which is exactly SD spec, but just in different physical form factor. So, and I had the one slide where basically the eMMC devices are MT devices on Android. Those have loadable firmware. They're known to have loadable firmware and can be modified.
Okay, as a follow-up, kind of unrelated, but I'm wondering if this, like the tool that you found was accessible enough that overclockers and things like that could kind of poke at the bad blocks and see if they were actually good and try and squeeze some more space out of the cards.
Yeah, you could probably try that. I mean, if you want to live dangerously. Like I said, the flash memory is already pretty crap, and so trying to eke out more space from your card by going into what are known to be bad blocks and use them for storage is caveat emptor, right? So, yeah.
Thanks.
Yep.
Microphone number 2, please.
Thanks for that great presentation. Did you look at SD cards that have embedded Wi-Fi?
No, we didn't look at those. Those clearly have a controller on the inside. And they run. I mean, they're known to run Linux and other stuff like that. We didn't look at those, but those are probably also an interesting target for hacking.
Microphone number 1.
Hi. Can you guess or estimate the market share about the AX215? Is it like 1%? Is it like 20%? How widespread is it? So.
Probably a tiny fraction of a percent.
Okay.
There's billions and billions of microSD cards made in the world per year. And the biggest players are SanDisk and Samsung. And those guys will sometimes buy controllers from smaller players like SMI and Apotec and so forth, but they never tell you which one's on the inside of those particular cards. They'll never reveal that. It's a kind of a trade secret for them. So they may have, I mean, they've made tens of millions, maybe hundreds of millions of these, but compared to billions of cards, it's a very small fraction still. So.
And another question from microphone number 4.
Yeah, just a remark about those Wi-Fi SD cards. A few months ago there was some story on Heise.de about some Wi-Fi cards with a fully fledged ARM controller, and it had Linux running on it, and I think they were pretty easily able to root it and turn it into some sort of Wi-Fi access point or some stuff like that.
Right.
And I think it has a really great potential for a little more interesting man-in-the-middle attacks and some other eavesdropping scenarios. So I think that's really something to worry about, especially if you think of a scenario where somebody relabels such a card and makes it look like a normal dump SD card.
Right, right. That's true. Yeah, and there's nothing that stops people from not using one of these controllers, but sticking your own, I don't know, take an STM32 or whatever and stick on the inside and label it as an SD card and just say, it's SD flash. People never take these apart, so there's a lot of opportunities there.
Okay, and another question from number 4.
Yeah, I want to kind of drag you off track here a little bit and see if I could get an update on the Novena.
That would be off track. We're gonna. Should we tell them about this?
You got it now.
Later on at 4 o'clock today, we're going to have one of those informal sessions where we're going to talk about Novena a bit. So I don't want to bore people here who don't want to hear about it with the details.
Okay. So where will that be?
I sit with the fail overflow crew. So it's in I guess in the hack center, Sol 3 all the way back. You see the big white dome, turn left, and we're sitting against the wall. If a lot of people show up, we might migrate away so I don't annoy everybody in the room with, and the people at my table. So.
Thanks.
Okay, so I'd like to jump in with a last question as well. Have you seen any SD cards that tell you there is a smaller number of memory inside, and inside there is like a huger chip, so you could actually reflash the chip and have a better memory card, like a 4 gig, and after you have a 16 gig memory card. Have you seen anything like that?
Yeah. I mean, a lot of the cards that we got actually have chips that are technically have 16 gigabytes of memory, but we actually, like, for example, we're finding cards that were sold as 128 megabyte cards, and they had 8 gigabyte memories, but they only had 120 megabytes worth of good sectors, supposedly. But you could reflash it and try to use all of them if you wanted to. You just probably wouldn't find you had much storage, actually. Just have random number generators. So.
Okay, so please have again a round of applause for Bunnie and xobs. Thanks again for your great talk.